Okay, this video goes over Objective 3 of ILM 302A, Introduction to Three-Phase Induction Motors. And what this objective does is explain how a three-phase motor operates. There are really two parts to this. The first part is the creation of a rotating magnetic field in the stator windings. So the stator windings will produce a magnetic field that turns, and that rotating magnetic field will cut across the rotor. And the second part of the operation of the motor is that rotating magnetic field cutting across the rotor and producing a torque in the rotor, causing the rotor to turn. So to start with the magnetic field produced in the stator, the simplest three-phase motor we can look at is what's called a two-pole three-phase motor. Each of the three-phase windings that are wound around the stator produce a set number of magnetic poles. And the easiest configuration of those poles to look at is a two-pole motor. In a two-pole three-phase motor, each phase winding is split into two parts and will produce a north and south pole. These phase windings are then connected in either a Y or delta configuration and brought out to the junction box on the motor. The simplest way to understand what happens with the magnetic field produced by the stator windings is just to understand that the three phase windings will combine to produce one strong magnetic field inside the stator. If we look at the sine waves of our three-phase windings, we have 3 voltage sine waves for our three-phase windings. If we look at those sine waves, we'll see that each one becomes a maximum value at a certain point in time. Whenever one of our phase windings is at its maximum value for voltage in the sine wave, it will produce the strongest north and south poles. The other two phase windings will work with the phase winding that is the strongest to help maintain this single magnetic field. When we look at the sine waves of the three phase windings and pick a point in time where the A phase winding is at its maximum voltage, that A phase winding will have the strongest north and south poles on our stator. The first half of the winding is wound to produce a strong north pole, and the second half of the A phase winding is wound to produce a strong south pole. The B and C windings also produce north and south poles that combine with the A phase winding to give us one strong north pole at the top of the stator, one strong south pole at the bottom of the stator. As we move ahead in time in our sine wave, we can see that phase C, 60 degrees later, is the next phase that has a maximum value. And that will cause the strongest north and south of our magnetic field to be in the C winding. So the main field produced in the stator has now turned 60 degrees clockwise from where it was originally. As we move ahead another 60 degrees, we will see that the next phase that becomes a maximum value is now B phase. And that will cause B phase to be the strongest north and south pole of our three windings and cause the magnetic field to shift another 60 degrees in a clockwise direction. As we go from A phase being strongest to C phase being strongest to B phase being strongest, this magnetic field produced by the three phase windings is turning in a clockwise direction. And you can see as you continue to move along in time in the sine waves that this progression continues, and A phase again becomes maximum, then C phase, then B phase, and this magnetic field just continues to turn in a clockwise direction. So that is what is happening in the stator, is the stator windings are producing one magnetic field that turns in a clockwise direction. To understand how this rotating field interacts with the rotor, we're going to quickly review a couple rules of magnetism. The first one is a left-hand rule for conductors. The way it works is whenever we have current flowing in a conductor, that conductor will be surrounded by a magnetic field. In order to determine the direction of that magnetic field, if we take our left hand and point our thumb in the direction of current flow in the conductor, our fingers will go around that conductor in the direction of the magnetic field. If we were to look at the current flowing out towards us, or if we think of the point of an arrow, that point here represents current flowing out of my conductor. And if I take my left hand and use my thumb pointing out of the page, my fingers will wrap around that conductor in a clockwise direction, and that is the direction of the magnetic field around that conductor. If I was to look from the other direction of current flow, view B, if I am looking at the current as it leaves and goes away from me, that is represented by an X, and that indicates current flowing away from me into the page. If I take my left hand and point my finger into the page, my fingers go around that conductor in the direction of magnetic field, and that magnetic field is in a counterclockwise direction. So we can always determine direction of magnetic field around a conductor if we know what direction the current flow is. The second magnetic rule we look at is the left-hand generator rule. And here's an example of how that rule would work. If this conductor was moved upwards through this magnetic field, the thumb of my three fingers on my left hand represents the thrust or motion of my conductor through the magnetic field. So the thumb would point up. My forefinger represents the field from north to south, so my finger points from north to south, and the center finger would show me the direction of the induced current in this conductor. Now to see how the rotating magnetic field interacts with our rotor that is situated right inside the stator, right in the middle of the stator windings. We need to remember that the rotor is constructed of conducting bars that go from one end to the other on the rotor, and at each end are joined by a conducting ring. So if there are copper bars that go from one end to the other, at each end there's a copper ring that joins all those bars together. This is what our rotor looks like. If we think of that rotor as sitting right in the middle of our stator windings, we can see how the rotating magnetic field will affect that rotor and produce a torque in it. If we use our three-finger rule and think of one rotor bar at the top of the page and one rotor bar at the bottom of the page, we will see that as our rotating magnetic field rotates clockwise across this rotor, as the magnetic field cuts across the top rotor bar, when we look at our left-hand generator rule with our three fingers, the thumb would point in relative motion of my conductor, and because the field is cutting across the conductor, relatively speaking, it is the same as the conductor moving in the direction the arrow shows. So if the magnetic field is turning clockwise, I would point my thumb to the left. My forefinger points in the direction of magnetic field from north to south, so my forefinger would point up, and my middle finger points in the direction of induced current in this conductor, which is out of the page. So with the rotating magnetic field cutting across this conductor, I will produce a current that flows out of the page at the top of my rotor. At the bottom of my rotor, I will produce a current that flows into the page because the magnetic field is cutting it in the opposite direction at the bottom of the page. So I have current flowing out of the conductor at the top of the page, current flowing into the conductor at the bottom of the page. The way that torque is produced on that rotor is now seen in the interaction of the two magnetic fields we now have. Our main magnetic field is rotating clockwise across the conductors in the rotor, and the current in the rotor bars will cause a separate magnetic field to be produced around each rotor bar as well. If I look at this rotor bar at the top of the diagram, using the left-hand rule for conductors, if my thumb points out of the page in the direction of current flow, my fingers will go around that conductor in the direction of the magnetic field. And what happens now is that magnetic field is in a clockwise direction. So on the right side of the conductor, that magnetic field is in the opposite direction to our main field produced by the stator, and it will oppose that main field, and lines of force will cancel out on the right hand side of the conductor because the magnetic lines of force are going in opposite directions. On the left hand side of the conductor, the magnetic field around that conductor is going the same direction as our main field and will strengthen the main field. It will combine with the main field to produce a strong magnetic push on the left hand side of the conductor, and we have very weak field on the right hand side of the conductor, and that will cause a torque on that conductor which tends to want to move that conductor towards the right. There'll be a strong push on the left side of that conductor, and it will tend to push right. At the bottom of the page, where the current is going into the conductor, the magnetic field around that conductor at the bottom is in a counterclockwise direction and is opposite to the main field on the left-hand side this time, and weakens the field on the left-hand side. But as it comes around the right-hand side of the conductor, it combines with the main field to produce a strong field on the right-hand side. And that strong field on the right-hand side of this conductor and very weak on the left side will produce a torque on this bottom conductor that tends to want to push it towards the left. And because all of these conductors in the rotor are connected together, the conductors on the top half of the rotor will all have a push towards the right. The conductors on the bottom half of the rotor will all have a push towards the left, and that will cause the rotor to turn in a clockwise direction. So the entire rotor will start to turn in a clockwise direction, which is the same direction the main magnetic field is turning, and that causes the rotor to begin turning and causes the motor to operate. And with no load, that rotor will speed up and try to catch that rotating magnetic field, and at no load the rotor will turn very close to the synchronous speed of the rotating magnetic field. And the interaction of these magnetic fields, these two magnetic fields in our motor, is what produces torque and causes our rotor to turn and allows the motor to operate. That's the basic operation of a three-phase motor.